that's never all that my ambitions are for class. It's never the only thing I want to do is to go through homework. I want to use the homework to reinforce some of the points that we've been talking about. And here's where I'm going to have fun, and hopefully you'll be okay with this. There's some stuff that we're going to do if I get to today that's going to help us slide into to chapter 4. And chapter 4 is a very big topic. It is very chapter 4 basically is about half of a course that I teach at the junior level, and so that I don't want that to scare you by any stretch of the imagination. I just want to set that into context. Now, the interesting piece about what I've been doing is, wherever possible, I've been foreshadowing what's going on in chapter 4 in this thing called Fourier analysis, and so there's a lot of what I already wanted to get across from a lot of what I wanted to get across from chapter 4. I've already done that, and so in the last couple of Mondays of the semester, I can sort of give you an appropriate introduction and awareness of this absolutely beautiful element of electrical and computer engineering, and one that really is so very foundational for how we look at how electrical and computer engineers look at the world, which is why I think it's fun to bring whatever part of that concepts at least into a first year class. There's a lot of formal pieces of the puzzle that we don't need to worry about right now. You might have to worry about that later on, but right now we can take the nicest part of the meal and enjoy those. So don't stress. It's all to the good. So the homework was about this thing that we called a transfer function, and we've been labeling this h of omega, and that tells us that the transfer function, or what happens from the input to the output, how the system transfers the input into the output, is a function of frequency. So different frequencies get transferred differently from the input to the output. So we did this with a voltage divider, and then we now have a frequency dependent current splitter. And so I've got a VN, and I've got an IN, and then I still have my two circuit elements that we've been playing with, a capacitor and an inductor. And now what I'm doing is, instead of arranging these in series, I'm arranging these in parallel. And so the current splits accordingly. And the impedance of the R is R, the impedance of the capacitor is frequency dependent. And it is this frequency dependent here that gives rise to the frequency dependence of this output over the input. And so the first thing to do is to say, okay, what are my two limits of this impedance? Just let's look at the circuit intuitively, and let's try to understand it quantitatively. And the first one is the DC components at omega equals 0. And in this case, that 1 over 0 goes to infinity. So the impedance of the capacitor is an open circuit. And so this circuit gets redrawn and there's no splitting of the current at DC, and all the current goes through the resistor. So all the current goes through the resistor. Let me label in I out here. And you can see that if I do that, I in is equal to I out for the special case of omega equals 0. Now, the other case we said was, we used to say that the other case was at infinity, omega equals infinity. I'm gonna use some imagination here and build on what we've done last time and be a little bit more specific about what I mean by a high frequency. So there's nothing a priori, there's nothing in this arrangement to start talking about our RC time constant, except for the fact that except for it's an assertion that may be right, may be wrong. But so let's sort of guess it, and if we're really wrong, well, okay, we'll back up. But I think we laid the groundwork for the high pass filter turning at a certain dimensionless number, omega RC, and we should have the same situation. So in this case, we're going to have essentially a short circuit for the capacitor. And this short circuit is R equal to 0. And so if I have a current, and I have a current that has to do work, takes some effort to get through R, and then goes down to the, or just takes an easy path to ground, that lazy current is going to go all the way down through the short circuit, and none of it is going to go down the resistor. Absolutely nothing. So in this case, I out is equal to 0. In this case, I out equals I in. And I put these two together. And what I see is that low frequencies go to the output, high frequencies do not. And so this is intuitively a low pass filter. Okay? And that's my intuitive analysis. It's my qualitative analysis. There's nothing, it's almost a guess at this point, except for the fact that I've been somewhat careful about looking at the limiting cases of the, I've been looking at the limiting cases of the capacitor. Okay, so this is, we've seen this before in terms of resistors. So we can start by just generalizing our results for two resistors in parallel, two impedances in parallel. Look like that. And the two impedances are the R for the resistor and the 1 over j omega c for the capacitor. Notice that I don't have to worry too much about whether the capacitor is Z1 or Z2 or the resistor is Z1 or Z2. The reason I don't have to worry about that is the beautiful symmetry that's in this parallel configuration. And so if you've got a capacitor and inductor and you solder them together in series, I'm sorry, in parallel, it doesn't matter whether you look at their circuit from the top or the bottom of the circuit board. It doesn't matter if you twist those around, they get turned around because some wire gets twisted by a customer or a technician or something. It'll still work the same. And that's kind of comforting if you stop and just think about that for a second. And so to simplify this, I'm going to multiply through by 1. And just to point out, you know, how many times in my lectures have I done something fun by just multiplying out by one in the appropriate way? And I always do that out explicitly. I always tell you that I'm multiplying through by 1. Other professors are not going to do that. Other professors are going to say, we're going to clear the 1 over j omega c from the 2 terms. That's fine, but I like pointing out explicitly what math we're doing to rearrange. And if I do that, then I get this as an expression for my equivalent impedance. Notice right away that the units of this are ohms because of the numerator. The denominator is dimensionless. I have a 1 that has no units, and I'm adding to it something else that I sure as heck hope doesn't have any units. And omega RC has units of 1 over time multiplied by time. You can quibble about the radians, and you should. But I'm not gonna spend too much time on that. And then oh, and notice also the presence of the RC. So I have omega RC, I have that dimensionless number X that I used in my Excel spreadsheets on Monday. And I'm also starting to feel pretty good about connecting omega with RC on that one. Because as soon as when I do my first trivial little thing, automatically pops up the relationship between omega and RC. Okay, so now what I want to do is I want to know I want to understand what my input-output relationship is. So let me write that as total, and then let me write this as I in Z equivalent, and then my I2 is actually my I out times R. And so I can write I out over I in. It's a perfectly good transfer function. It doesn't always have to be voltage. We just have to remember that if I use this and I multiply through I multiply through by an IN, I need to figure out I need to figure out what my that I'm multiplying by I and I'm getting an I out. And so if I then want a voltage on the outside, then I have to look at my resistor again. Let me do something a little bit. Let me emphasize that this is going to be a function of frequency. And the reason for that is this is going to be Z equivalent, which is a function of omega and R. And so this is going to equal 1 over 1 plus J omega RC. And this is very similar to what we had before, but there's no omega in the numerator. Same denominator as before, as our high pass filter. And so now that I'm very clear in my two limits, at omega much less than RC, than 1 over RC, H of omega equals 1, and at omega much greater than 1 over RC, H of omega equals 0. So I have H of omega is equal to 1 over 1 plus J omega RC. I'm multiplying by 1 again, the complex conjugate of the denominator. And we looked at this weeks ago, so we know this is how we clear the square root of -1, the J, from the denominator, and therefore we're able to separate out H into a real and imaginary part, so that we're able to calculate what our phase response is and what our magnitude response is. And so this is equal to 1 minus J omega RC, and this is 1 plus omega squared C squared R squared. The phase as a function of frequency, the phase response that each signal gets as it goes through this device, and I was trying to remember what we got for the other case, but I believe for the high pass filter, this was 1 over J omega C RC. And so for the slow pass filter, we have the flip of that. And then H of omega magnitude is going to equal the square root of 1 plus omega squared R squared C squared divided by the square root of that quantity squared. So I'm going to clear out that R squared C squared. So I'm going to square it and then take the square root. And this is equal to 1 over the square root of 1 plus omega squared R squared C squared. And again, there's no omega RC in the numerator. If you remember last Wednesday's lecture about transfer functions and feed forward and feedback, there's no B's, no feed forward in this transfer function. there's only A's and feedback. And just to level set, I have no expectations that you're remembering that right now. I have no expectation that you remember those A's and B's from last Wednesday. And that is precisely why I'm bringing it up today. So that I remind you, I get you all tense and nervous, and I remind you of something that we did cover, and maybe that helps us reinforce some of these concepts. All right, so that's where we need to be for the next step, which is I want to go back to the Excel spreadsheet, and I want to show you where how to plot that. The things to plot is this function for the phase and this function for the magnitude. Okay, and what we're going to see is a low pass filter. And so let's just run to our Excel spreadsheet. We're going to do this coding correctly. Stop share. Share screen. Here's what we have. So okay, so and I'll send you these spreadsheets. I'll send you these spreadsheets Friday at the latest. Rasik, if I haven't done it, would you? If I haven't done this by Friday morning, would you send me a note? Or maybe Matthew. I'll get Matthew to help me out on this. Matthew, if you would send me a note on Friday morning, I'll make sure that this goes out, and that way I get to hear from some of you guys. All right. So here's the same frequencies that we had before, and I'll just remind you that this X here is the number omega RC. So the frequency, the way we say this is the frequency is normalized to 1 over RC. That's a term of art. And what that means is this 0.1 in cell A11 is the precise point at omega equal to, that's the precise point that omega is equal to, let me go here, sorry. That's the precise point that omega is equal to RC. And so here's our plot of the transfer function. Notice that it's just 1 divided by the square root of 1 plus x squared, or 1 plus omega RC quantity squared, all raised to the 1/2 power. And we'll see that when we get to 1, really hard to read, but it's sort of right down in here. It goes to 0.707, which is this little kink in the line right here. I wasn't very good about oversampling. I have sort of the minimum number, but some of that's okay because that allows me to see those data points. And so this number 1 right here is 0.707, 1 over the square root of 2. And so here's the linear plot as a function of frequency from much below for 2 decades. Remember that term, 2 decades below the RC, and then 2 decades above the RC. And then I told you that since we're covering 4 orders of magnitude in frequency, 4 orders of magnitude in frequency means that we like to do a log plot of our frequency. So going between 0 and 1 on a log plot, going between 1 and 2 on a log plot is an entire order of magnitude. It's an entire order of magnitude. So I start 2 orders of magnitude. So the RC equal to 1, I'm sorry, the omega equal to RC, this point here at x equal to 1. If I take the log of 1, I get 0, because 10 to the 0 is 1. So 10 to the 0 is 1. So log of 1 is 0. And so this is my turning point. This is my pivot point right in here. And you see that that comes up on this scale there. I'm easy to read. That's 0.707 number right there. I go a decade below. That's what we mean by much greater than, is a factor of 10. Much greater than is usually considered to be a factor of 10 or more. Much less than is usually considered to be a factor of 10 or less. And so certainly right around here, we have full transfer of the current going through the resistor to get an output current over an input current of 1. This is sort of an interesting area between 1 and minus 1, a decade below to a decade after. That's sort of this middle ground of transition. And then we have rejection after we get to about an order of magnitude higher than the RC. So this is, in fact, passes low frequencies, lower than 1 over RC, and it filters out where it sends the higher frequency currents to ground in this regime here. And so then if I have so much fun with logs on the x-axis, why can't I do that on logs on the y-axis? And when I do that and multiply by 20, here's 20 log of h of x. Then what I have is called a Bode plot. And if you look at this Bode plot and you look at the high pass Bode plot, they're exactly a flip around the axis. So if you add one to the other, you'll get if you add one to the other, you'll get a flat line across. If you multiply one by the other, you get a really interesting curve that kind of does this, kind of peaks around RC equal to 1. So those are a couple of foods for thought right there. What gets passed what doesn't get passed gets rejected. What doesn't get rejected gets passed. For both of those. Now, so this is just 20 log. 20 times 0.7 is 3. Is that right? Yeah, I think that's right. No, that's not right. Anyway, I'll have to double check that. It is what it is. I'm doing 20 of the log of 0.7 is equal to -3. So what that tells you is that's called a 3 dB point. So the filter response is down by 3 dB. It's down by 3 dB at the RC time constant. And here's my 20 dB per decade Here's my 20 dB per decade slope on the roll off, this time on the high side, not on the low side. And then here's my my phase response, and it's completely flipped from what it was before. Let me see if I can go back to that. I renamed it, sorry. So notice before I started at pi over 2 and I went to 0, and that's for my high pass. And for my low pass, I dropped this down so that it starts at 0 and it goes to minus pi over 2. Okay, so we're seeing that matters. We're seeing that 90-degree phase shift flowing in on the rejection side, and we see a 0 phase shift floating in, happening wherever we have a pass band. Okay, so like I said, I'll send out this stuff Friday, notes, and also these graphs. And now you see why I didn't send this out, because it was so trivial to just go in there and change the low pass to the high pass, that I wanted you guys to stress a little bit and learn a little bit more about that. Okay, yeah, so let's see. Go back to my notes. And now I'm going to freak you out a little bit and do some new stuff. So, and this gets us into a little bit of thinking about chapter what's coming up in chapter 4. We probably won't get all the way there today, so some of this might flop over into Monday. But what I want to do, oh, and this also gets us into some math that I know some of you haven't seen formally yet. But I don't think there's going to be any problem. I don't think there's going to be any problem with how I'm going to treat this math. I think if anything, this is just a little bit of awareness that will end up helping you as you go down. So none of this is going to. Yeah. So this might get into some math that's a little bit tricky, but I'll walk you through it. And I'm very much aware of the fact that this could potentially be new to you. So here's my output, and the current that flows through this resistor is equal to V over R. And here's my capacitor. And capacitors work, the fundamental rule of a capacitor relates Q to the voltage, the charge that this capacitor holds. And so in order to make sense of this, I take the derivative of both sides of those. And so the rate of change of the charge on the capacitor becomes current this is coulombs. This is coulombs per second. And an amp is equal to coulombs per second. On the right-hand side, I've got voltage per second. Capacitors are measured in farads. So I can go from farads to volts and coulombs. I can see that a farad is equal to a coulomb per volt, both in this expression and in this expression. And it's important to note that when I take d by dt of both sides, I'm assuming that my capacitance is not a function of time. And since my capacitance is metal with some polymer between it, as long as that polymer doesn't break down or change quickly with respect to time, this is a reasonable statement. How are we doing for time? Okay. So Kirchhoff's current law, current in the capacitor plus the current in the resistor is equal to the current in. Let me write that. Let me not worry about those little letters. Let me just write that as I current is equal to I resistance, plus is equal to I in. It's the role of the current splitter. The change in the voltage on the output plus 1 over RC on the output is equal to I in over the current. So that's another way of writing my current splitting equation. So I dV dt here, V out over RC times this. So what I'm going to write this as is V out is equal to RC times I in over C minus RC times dV out dt. And so now I can write I out is equal to V out over R, which is equal to I in minus C dV dt. And really, this is probably the easiest thing to relate to this. I out, I in, dV dt. And so if I look at this term here, and this term here, I can draw I in to I out. So what I can do is I can draw my signal flow diagram. And I can write my output in terms of my input. And notice that this plays the role of a j omega. It also plays the role of that delay. The charging of the capacitor and then the discharging of the capacitor gives you a frequency dependent delay or the phase shift of what's going on. And you'll notice that fundamental to this, all that crazy math that I did tells me that this actually is a feedback circuit, even though there's no way you'd ever think that until you go through that tortuous math that we just did. Okay, so this you'll study these equations, you'll study RC circuits, and it's always going to be hidden from you in most typical courses that you can draw this in a signal flow diagram, and you can draw this as a feedback, and fundamentally as a feedback. And that's why, in fact, we have this denominator. That denominator comes from a feedback 1 plus beta A. Okay? Just like we talked about in the biggest abstraction. So the equation I want to turn to is this one here. And this is the equation that all I did here was put in the terms for the current where they went, and out popped this equation. But where everybody will get upset is that what this algebra, what this simple derivative and then what the algebra followed did was give us a differential equation. And all that is an equation, an equality that has derivatives in it. And at this point, I will never ask you to solve a differential equation. I will never burden you like that, because I know that that's really unfair because you haven't seen it before. But it's so simple to get there. F equals ma is a differential equation. So there's plenty of, we might as well just call it what it is, which is, a differential equation. And you're going to have plenty of time to practice across the next few years how to solve differential equations. And so really this is just towards the end of the semester. This allows me to kind of get you looking forward a little bit. Now, this term here is the forcing term. And so the first thing you do when you solve differential equations is you get rid of the forcing term. You get rid of the forcing term. You solve this equation. This is called the homogeneous or unforced differential equation. And then you have to solve that subject to some sort of initial conditions. So to solve the differential equation, you guess the solution. So you guess a differential, you guess something that's e to the minus t over tau. And in class, you always guess right. You don't always guess right on homework or in the real world. And I will give you the answer and then we'll quit for the day. When I substitute that in and I solve for tau, I get tau equal to the RC time constant. So that RC time constant comes about in this analysis just like it came out in the algebra. Notice that guessing this solution here, this exponential solution, is very similar to guessing the exponential solution when we first looked at that c dv dt to get to our complex impedance. All right, I'm going to quit there because we're 2 minutes from ending. I'll pick some of this stuff up next time on Monday. I don't care that you learn all the details of the math right now. I know you don't have. I know that you don't have differential equations. Some of you do. Some of you don't. It's okay. If you haven't seen it, this is an easy introduction to it. It might make sense later on down the line. Or you can just rest assured that this is just for fun, there's no, I'll never ask you on an exam to do this. So with that, I'm going to stop. I'm going to,